We continue our topic of kinematics of serial manipulators or serial kinematic chains. So remember, we have something like this. We measure angles from the previous link counterclockwise, at least in textbooks. Okay, and if we write a vector equation for this and put it in component form, roughly, we see that for a typical 6 degree of freedom robot, which has 6 independent coordinates in the task space and corresponding or 6 inputs in the joint space, the connection that describes the geometry is a set of 6 equations with a lot of nonlinear or trigonometric functions in them, and that the red forward problem is trivial because you just substitute the joint angles into the right side and you get the position of the end effector. But the inverse kinematics is difficult because you have things here on the left side and you need to find all these angles that are hidden inside the nonlinear functions. Okay, and then we also mentioned that for this general case, the solution can be found only when the last 3 axes intersect in a single point, and that is why robots are designed and built in such a way. So 6 degrees of freedom robot, first 3 axes move the center point of the tool, and the remaining 3 axes rotate the tool around that center point. So they call it a decoupling. Translation, decoupled from rotation. Now, let us consider a simple case of a 2-link manipulator. Okay? So we need to do it first to sort of introduce you to the methods that pop up in robot kinematics, and second of all, during the lab you take measurements with certain joint angles fixed. So in the end, the equations for the 2-link manipulator will be applicable for your lab and should be used in your lab report. And if anyone wants to go to the source, there is a book by John Craig, Introduction to Robotics. And this is the best introductory text on robot kinematics, dynamics, and control. Okay, so the mechanical sort of side of robotics, not the artificial intelligence side of robotics or things like this. Okay, so we have XY coordinates for the end effector, and we are looking for joint angles θ1 and θ2. Okay, and these are therefore the equations, that is the projection of this simple vector equation to coordinate axes. Okay, so these guys on the left are known. We are looking for the angles that are under these trigonometric functions. So now I need to introduce a bit of the robotics slang. Okay, so in robotics, usually they don't use R for links, but L. So this green stuff is like using mechanisms slang, and the blue thing is using robotics slang. So L1 is R1, and C1 is cosine θ1. Okay, and S1 is sine θ1, and S12 is the sine of θ1 plus θ2. Okay, so this is the notation that is common in robotics. C for cosine, S for sine, and if there are more than one numbers here, it means that this is a sum of of angles. Okay, and there are a number of ways or standard ways to solve this problem, and the one that I will be showing is called the so-called algebraic solution. Okay? So, I suppose it is not very clear how to solve this set of equations for unknown angles, theta 1 and theta 2. So I'll just tell you the trick. The trick is, and you may recall that a similar trick we used already for a 4-bar, is to square the equations and add them together and hope for the best. Okay? So we are squaring equations and adding them together, and we are getting something like this, right? So from the first one, it's x squared, and on the right side, L1 squared, C1 squared, L2 squared, C1, 2 squared, and then 2, L1, L2, C1, C1, 2. Okay, and similar stuff from the second one. Now, we can see that some things begin to look familiar, right? That the stuff underlined with red is S1 squared plus C1 squared, which is 1, right? And the stuff underlined in green is S1 2 squared and C1 2 squared. If you add them, it's 1, okay? So, if you do this addition, so the red stuff is this, the green stuff is this, and now if we use equations for the cosine of the sum of angles and sine of the sum of angles, we get something like this. So 2L1, L2, which is this guy, plus, and in brackets, stuff that comes out from expanding cosine of a sum of angles and sine of a sum of angles. And if you do this, you get lucky, because this guy cancels out with this guy, and this guy, again, sine squared plus cosine squared is 1. So you get this very simple expression in the end. Yes?
Isn't that just the length of the, isn't that just the distance between the end effector and the origin?
This, well, the squared distance, right? Because square root of x squared plus y squared is a distance. It's this. R is this. So obviously it's a distance, right? So this is how this algebraic solution works. Some people perhaps would be able to find a different approach, but this is sort of standard. Because in many situations in geometry of robots, when you do these squaring of equations, you end up with things disappearing and or simplifying. Okay? So this is our result for a cosine of theta 2, right? X squared plus y squared, something with dimensions divided by, again, something result dimension. So for a given position of the end effector, you get the cosine of theta 2. Now, silly question. How to extract the angle from this? We have the cosine of the angle. How to get the angle? Arc cos we would do by hand in the primary school, but if we consider that we want robust methods that can be programmed on the computer, then arc cos would not be so good, because how would computer know in which quadrant to pick the angle, right? So there is one more thing. If we do it at home by hand in a piece of paper, there is no problem when we get some strange value on the right side. But if it is done by a computer, and the right-hand side is outside the range of a cosine function, which is from -1 to 1, we will get into serious trouble, right? For that red equation to make sense, the right-hand side must be between -1 and 1, because this is the range of a cosine function. So, which means that in a code doing this, before proceeding, one needs to confirm that the right-hand side is in this range. Because if one just goes on, then nonsense can be received, or, for example, using MATLAB, when imaginary numbers are produced, MATLAB usually retains just the real value and neglects the imaginary part, and it all looks good, except that it makes no sense, right? So this needs to be checked. What does it mean if the right-hand side is not between -1 and 1? Sorry? Cannot reach, exactly. So the x, y that we specified for the end effector are outside the workspace of the robot. So cannot go there. Okay? So in the code, we would have a line, check this condition, whether it's between -1 and 1, and if it is not, computer spits out the comment, sorry, the point x, y for the end effector is outside the workspace, please try again. Okay? So the robust way of dealing with extracting the angle is, rather than doing arccos, is to first compute the sine, which is square root 1 minus cosine square. And here we decide with sigma, which can be +1 or -1, whether we want elbow up or elbow down configuration. Okay? The same position of the end effector can be reached with the elbow up or elbow down configuration. And this is decided here by that +1 or -1. Okay? So when we have decided this, then we extract the angle, θ2, very quickly using a two-argument arctan function that we already discussed before. So when we just put the sine and cosine of the function as arguments. Okay? So this is the robust way of extracting the angle and deciding which angle to take. So we now have the angle θ2. The next we need to find the angle θ1.